Hola, it's Alexis's podcast again. I've done this a lot. But podcast number 3, nice picture. Let's get started. So, for numbers 1 through 4, we're going to use this graph to answer some questions pretty much. So for number 1 and 2, we're asked to use the continuity checklist to determine if the function is continuous at these values. So our first value is x equals 2. Let's see our graph again. Okay. So at x equals 2, our first question we're going to ask ourselves from the checklist is, does f of 2 exist? Let's see. No, it does not exist because there's an open circle, so f of 2 is actually undefined. So it fails the first question of our continuity checklist. For number 2 on the checklist, we're going to ask, does the limit of f of x as x approaches 2 exist? So let's see, from the left we look pretty good, but then from the right, no, the numbers are not the same. From the left and the right, the graphs don't approach the same value, so we know that the limit of f of x as x approaches 2 does not exist, so it fails number 2 as well. And number 3 is going to ask, does number 1 and number 2 equal each other, and they do not. F of 2 does not equal the limit of f of x as x approaches 2 because there was no value, so no. The point is not continuous when x equals 2. At x equals 2. Okay. So for number 2, we're asked to do the same thing for x equals -4. So let's find our -4, which is over here. So our first question is, does f of -4 exist? Let's see. There's an open circle here, so we know that for number 1, it's already failed that piece of it because at x equals -4 is undefined. Number 2 is going to ask, does the limit of f of x exist as x approaches -4? We see that from the left and the right, the line here approaches the same value. Even though it's open, it's approaching the same value. So yes, that value does exist. However, once we get to number 3, we see that we're going to be asked, does number 1 and 2 equal each other? And no, they do not equal. So neither of our points have been continuous thus far. Well, not thus far because those were the only 2 points we had to find it out for. So no, for number 1 and number 2. For number 3, we're asked, does f of -1 exist? Let's see. I guess -1 would be somewhere around here. And yes, there is a point. Well, there's not a point, but there's a value here for the graph. So yes, f of -1 does exist. For number 4, we're asked, is the function defined at x equals -2? Well, first we have an open circle here, but there's a closed circle, so that means that our function is defined at f equals -2. Well, at x equals -2. So yes, the function is defined. I forgot this one last time I did the video. So how are continuity and domain related? So pretty much, well, let's use our graph for an example, but the domain tells like the intervals for which like a point is continuous. So we can see that, just for example, here from 4 to pretty much infinity, the function is continuous. I don't know if that's a good number. If our points were at 4 and 6, and there was an open circle here, then at from 4 to 6, which would be our domain, I want to say, our points would be continuous. But pretty much, continuity exists inside of a domain. Alright. So for number 6 and number 7, we're asked to determine where the functions are continuous at. And pretty much we know that we have a radical in our functions, so we're going to see what values are going to be possible for us to have for that radical in our denominator that we could have as an x. And we know that because the radical's in the denominator, it can't be negative and it can't be 0. So we're going to set this, well, not equal to 0, but greater than 0. And we're just going to find the numbers in the denominator that it could equal because that's what it is. So 8x minus 2, if it was greater than 0, let's find what numbers would be greater than 0 to give us a number that would be continuous. And there's an airplane. So it's just pretty much simple algebra from here. So we're going to add 2 on both sides. And that's going to be 8x greater than a positive 2. And divide it by 8. So we're going to be left with 8. X is greater than 2 over 8. 8. Which would also be 1/4, which would also be a quarter. What? A quarter. 0.25. So that's going to be my answer for that. So if our x is greater than 0.25, then the function would be continuous as long as our x is greater than 0.25. That's what that's saying. Oh, if I could get my words out. So for number 7, we're going to find the same thing, determine where the function is continuous. So we know that pretty much in the denominator at any point it's going to be continuous as long as it doesn't equal 0. So we're going to try to find what x is going to make our function equal 0 pretty much. And at those points it's not going to be continuous any longer. So we just have to really pretty much consider the denominator. So x squared plus x minus 42. And we're going to factor. Guess who knows how to factor now? So we want something that multiplies to equal -2 that would add to equal 1. And we know those numbers are going to be -6 and 7. Because -6 plus 7 equals a positive 1, which is what we were looking for. So pretty much just put your x's in parentheses. And then put those 2 numbers that you just found. Little factoring lesson. And for each of those numbers, for each of those values in parentheses, what will make them equal 0? And we know that would be x equals a positive 6 and x equals a -7. And like we said earlier, it's going to be pretty much every value except for when x equals positive 6 and x equals -7. Except. That's how you spell that. And that's our answer. And that's my podcast. Hooray!